Okay, so welcome to everyone, and it's a great pleasure to me to introduce the course by Gian-Michele Graf. Gian-Michele is a professor at ETH Zurich, and he's an expert in fundamental properties, thermodynamic properties of quantum system. In his career, he has worked on several problems spanning from the proof of the stability in quantum theory, stability of matter, in quantum theory, going through many body scattering problem, quantum pools, and various problems related to solid state physics. And more recently is working a lot on topological properties of matter, and that's why we feel very honored to have him for our semester here at JSSI, and he will give an overview on matter and topology. So thanks a lot, Gian-Michele, for your presence here and the ability to discuss.
Thank you, Serena. So my part, I also wanted to thank you first for the great hospitality here. It's about the months now that I've been enjoying a lot. But you know, beyond this personal aspect, here is my thought. I thought you were one of the people who came to GSSI at the earliest after its foundation. And by doing so, you contributed to the resurgence of this town, making it a place that is hospitable and worth living to many, not just occasional passers-by like me. So I think this is a that great thing you're deep and you're still doing here. So the next thing is, Serena just said, ask questions. Whenever you feel ask questions, if I should turn my face to one side and just speak. That's like, no. Let's move to the first page. It's not the accent.
Just click on the slide. Sometimes it's pages.
Oops, no, it backed it too much. No, so I'll do it back to the lower button. Yeah, but one by one, obviously. One by one. But it's the place of two.
Maybe
It's something happened here. Let me what I'm going to tell you about today is joint work with generations of graduate students and postdocs. There are the names, and also some people older than me, even whom I learned a lot on the last line. So here is an outline of what I would like to tell you. Maybe we're going to change. But first, I would like to start from a physics overview, physics background, and give you, a rapid view from the beginnings to more recent developments. And then, starting from the second chapter here, we go back to mathematical topics first, back to the quantum Hall effect, where all began, and then we will see it in various ways, various geometric tools, vector bundles, and there could also be non-periodic settings, and then we'll move on to other topics well beyond the quantum Hall effect. So I chose not to speak primarily of the recent results and to give the proof or anything like that. If you hope for something like this, not as I planned, then just tell me. There are more days to come, and we can still change the program if you like. So here is the overview of the first thing in the first chapter, and I'm going to tell you about the integer quantum Hall effect, where it all began. And so here is the first thing. That's not even quantum Hall effect. That's just the setup of the whole effect without the quantum. So what you see there is a metal foil, perhaps gold, here, and the perpendicular magnetic field. That's a view from the side, and if you view it from above, it looks like this. And if you could look microscopically, then you would see edge currents that run along the sample, equal on all sides. Nothing is carried in or out, and it would look like this. Then you may attach leads to this sample. For instance, on the sides here, leads for the current, so it can come in and out. And on the other side, leads where you apply a voltage, maybe also as a result of that, current start to flow. So what do you expect? Well, you expect that if you apply a voltage, a bulk current starts to flow in the direction of the applied voltage, right? If you apply a voltage to a cable, the current starts to flow in the direction of the applied voltage. That's the most natural thing to expect. What else would you expect? So there is this longitudinal current that flows, but there is also current transverse to it, which gets in and out. And if you were to look closely inside, the edge currents, which were before equal, if you want, opposite on all sides, now they are unequal on opposing sides, and this contributes to the net current that comes out. Okay, and now we come to the quantum Hall effect. That is now the change I'm about to describe. And then what so happens is that if the magnetic field lies within certain favorable ranges, not all values are good, but some values of the magnetic field, then no bulk current flows anymore, and there's just a transverse current left. Oops. So it goes this way. And in other words, the metal, which was given by the fact that the current would flow in the direction of the applied field, no longer does that, and effectively it has turned into indices. And the edge currents do no longer change with the magnetic field. Before, I failed to say, if you were to change the magnetic field, these edge currents would change, but now they no longer change within these favorable ranges. And a more precise statement would be that there is no longitudinal bulk current. Perhaps there is some bulk current here, and the way this transverse current, whether it is edge or bulk, may vary. Some may flow in the bulk, so transverse, and some may flow on the edge. It's somewhat a matter of debate, and something that you may well ignore for now. It will come up later. So here is a plot of what you see when you have this magnetic field plotted here horizontally, and these favorable ranges are depicted here in green. And then there is no bulk current, and that is signaled here by the fact that the graph is at zero. No bulk current flows. That is the vertical bulk current or longitudinal bulk current with respect to the applied voltage. And here you see the edge currents, and within these green ranges, it's absolutely constant. In fact, constant with an accuracy of 10 to the minus 10 or something. And that conductivity is associated to an integer, and that integer is a microscopic problem. That is an astonishing thing. You know, in quantum mechanics, we are often used to start with the harmonic oscillator. The levels are integers, also hydrodynamics, they all come with integers. But the thing is that these integers occur only in the limit of infinite largeness. So it's an emergent property. That's unusual for quantum mechanics. So let me introduce some concepts that are attached with quantum Hall effect. So here is the sample again, viewed from above. We just introduce some coordinates. And there is the magnetic field which is out of plane. There is an electric field in the plane. There is a current density, which in the ordinary Hall effect may also flow in part longitudinally, in part transversely. But here it's already depicted this ideal case when it flows transversely only. And there is an electron gas, and there's a parameter characterizing this electron gas. We need the density. So how many electrons there are per unit level will come up in the next slide. Now there is this whole Ohm law, which is just a phenomenological law which tells you the proportionality between the current and J. So proportionality just means linearity, so I should say it like this. Doesn't mean that it's parallel. Therefore, the linear relation between the two is given by a matrix, the conductivity tensor, and it has two parts, a diagonal part, sigma d, which is isotropic, at least for simplicity, and an off-diagonal part, the red one, with sigma whole, which is anti-symmetric. So there's the whole conductance and there's the longitudinal conductance. And you could also speak of them in terms of dissipation. So when you have a current that flows through matter, like the current flowing in this wire, it heats up a little bit. That's called the Joule heat. So what happened here? That's the Joule heat. And you can compute how much heat is produced per unit time and unit area. That comes from electrodynamics. So if you have questions on the electrodynamics, actually you can deeply write the backbone explaining where this comes from. If not, this is an accepted fact. And if you insert the J we get from the whole Ohm law, you see that the part which is perpendicular does not contribute. The part of J that is perpendicular to E does not contribute to the single product. Only the part that is parallel, and that's the sigma d part, contributes, and the result being sigma d squared. So only that part, sigma d, contributes to dissipation, and the whole part does not contribute to dissipation. So this can also be called the dissipative conductance and the dissipationless conductance respectively. So again, the density of electrons is 8. This time we need it. Here is the whole Ohm law. And the line there is just to say that this comes from the previous slide. And ideally, we assume that the dissipative part is 0, so J ends up perpendicular to the E vector. And it is an explanation how this comes about in presence of a magnetic field. There are charge carriers, electrons, but it could also be holes. The charge of each of them shall be called Q. And they have a velocity V, and they experience a Lorentz force, which is given by this hopefully familiar expression there. And so you can ask, what kind of motion does this generate? Let's start with equals 0 for simplicity before. And then, so then the force is perpendicular to the velocity. So it's a centripetal force which causes a circular motion. A circular motion like you see it here. And that's the trajectory. But if there is an applied E field, then on this circular motion, the charge is accelerated, and then it goes faster. It's accelerated, let's say the charge is -1, then it's accelerated like this, opposite to the electric field. And its radius of curvature becomes larger, but then it turns, it moves against the electric field, it slows down, its radius of curvature becomes smaller, and the net effect is a cycloidal motion moving to the right, like you see there. And so this equation is also valid if you replace force and velocity by the average, since it's a inhomogeneous relation. And let's read it like this. So in the first case where there is no electric field, then the average force in this case will be 0, and also the average velocity will be 0. There is no long-term motion here. But in the other case, simply I did not show the slide here. So if E is 0, you get J equals 0, so as expected. But if E is not 0, and the force is still to be 0 on average, because we are talking of the stationary regime, then the two terms cancel one another. And since these two vectors here are perpendicular, and if you just look at the magnitude, E and B have to be in this relation, with V over C as a factor in between. And then this generates a current. So how does this come about? Each of these carriers has an average velocity V, and they populate the plane with a density N, and each of them has a charge Q. So that's the current density J that flows in that. So here is from the previous slide. And then we can compute two quantities that are characteristic from these experiments that are measured. One is the whole voltage. So you you measure the voltage from one side of the sample to the opposite one. And so let's call D the width of that sample. And so the whole voltage is just the electric field times the width. And the total current flowing across and eventually out of the leads is this current density times the width, the same width D of the sample. So you get these two quantities. And then there is the whole resistance that defined like this usual Ohm's law, except for the fact that now current and voltage drop are perpendicular to one another. But it is V over I. And if you insert expressions, you see that the width of the sample cancels. That's also E over J. And E is given by, can be replaced by this expression here that sits here in the numerator. And for J, the denominator, you write this expression, you see that V cancels. And that's the final result for the whole resistance. So it no longer depends on E, because both the whole voltage and the current are both proportional to that, and this cancels out in the result. So here are a few remarks or predictions that one could, predictions of this theory that in fact I have been tested. One is that this is the whole resistance. The whole resistivity would be the quotient of intensive quantity, like the electric field and the current density. Well, it's the same thing by this equality here. This would not be true, this property would not be true for longitudinal resistivity and longitudinal resistance. That's peculiar to the whole. So I'm still not quite used to this. And then this whole resistance gets large for when the density is small, the density of electrons per unit area, that makes thin foils. It is more general proportion to B over N, but it would be interesting also to have the proportion to B for 1 over N, so if the other is fixed. And then it can be used to determine the sign of Q. It will tell you whether the carriers are electrons or holes. These are just a few physics facts, well known facts about resistance. Now, let me say something about conductivity versus resistivity. It's at first it's a little bit striking. It already came up in a sense. It suffices to put in the ideal case just a tiny little bit of magnetic field to make the current that was running longitudinally completely absent and have totally cancelous. So an arbitrarily small change could change the picture completely. Let's see how it comes about mathematically. So here is the whole Ohm relation again, and you can invert it, that is expressed in terms of J, by the resistivity tensor, which will be the inverse of the conductivity tensor sigma, right? And so as tensors, they are inverse of one another, and if there is no Hall complex, no magnetic field, and sigma Hall is zero as we're used to, then the inverse, and the matrix is diagonal, and the inverse is just element-wise on the diagonal. So, for instance, a very good conductor, one where sigma D is very large, with a very large conductance, has a very small or even vanishing resistance. That's how we are used to. But if sigma Hall is there, right? Now there is some off-diagonal non-zero matrix element, then these two things are equivalent. It's no longer these quantities are inverse to one another. But if sigma D is equal to 0, then also rho D is equal to 0 and vice versa. For a very simple reason, that if this matrix is anti-symmetric, then also its inverse is anti-symmetric. Is element-wise the inverse. So if sigma D is equal to 0, that's the ideal case, then also rho D is equal to 0. And in this case, I think I said it, the off-diagonal elements are the inverses of one another. So, you know, it's here that one is 0 and the other is 0 are mostly consistent fact. One is 0, goes with the other is infinite. But if sigma h is not 0, then they go along. So the moral is that an arbitrarily small p field, which turns sigma h into non-zero, turns a formally perfect conductor that is 1 with 0 resistivity. It's in there. Here. Right? It's some line, but anyway. It's still there, but then it goes along with sigma d equal to 0, and that's a perfect answer. Now, this is now let's come closer to the quantum Hall effect. This is a picture of a device. It's no longer that gold foil that you saw at the beginning. It was a glass Hall effect. So you still see this whole bar here. And then there are leads attached on the left and on the right. And here you can put on some voltage if you wish, measure some currents also in the longitudinal direction, and do all kinds of measurements. This one is done with a foil of graphene. And there have been earlier devices going back all the way to the 1980s, which were based on heterostructures, that is different semiconductors in layers. And in the boundary between the two layers, there was an electron gas, which was responsible for the thing I've been just talking about before. I think that may suffice as a picture. Let's move on to the next slide, and let me try to explain how this integer quantum Hall effect comes about. So here is the picture of before, but as a characterization of the electron gas, I introduce the Fermi energy. It's the distinctive quantum picture. So what's the Fermi energy? We imagine that all particles depend upon another. It's a simplifying assumption, but in many contexts, one. And that they feel energy levels from bottom up. And the last level they feel is the Fermi energy mu. So if you increase the Fermi energy, sorry for this back and forth. If you increase this Fermi energy, then also the density increases. But the point, as we shall see, is that the increase of the two is not strictly monotonous. This will be very important. So for the rest, you see the same notions as just before. And so here is what you observe as a function of. So the first slide I showed you, there was resistivity as a function of B, but we may take the inverses of both. So it's conductivity, or conductivity, as a function of P over N. So we can plot it as a function of this. So as more and more, as the density increases, which can be tuned, sigma Hall increases. The classical value would just be that it's proportional to N. Right? It would be this diagonal line. That's the classical curve. But the experimental curve is something like this, but it exhibits this plateau, which in a slightly different diagram we've seen before. And here downwards, you can also plot once more the direct conductivity. And whenever you are in one of these favorable regimes, it turns to 0. Then it's something different when you're outside these favorable regimes. And the interesting thing, which we'll comment upon, is that these plateaus wouldn't be, strictly speaking, present in a perfect system. They are there because there is some disorder in the system, and in fact, they tend to increase up to some point as the disorder increases. And again, the experiment is astonishing in the accuracy of the constancy of this plateau, and you can compute measure the value of this whole conductance. So here I forgot to say something. Here it is plotted, and the natural units in which the plot is E squared over h. So E is the charge of the electron. H is Planck's constant, or sometimes thinking as 2 pi h bar. And if you put E and h bar to 1, then the value of this thing is 1 over 2 pi. So in these natural values, this sigma h is quantized, takes integer values in units of 1 over 2 pi. And from that, you can infer what the combination of fundamental constant of nature E and h is, this constant. and you find this value here is an astonishing number of digits, of significant digits. So there is another Hall effect that is not in the picture that I thought I just showed you. It's called the fractional quantum Hall effect. And it's roughly the same thing. Here they plot the magnetic field and the resistance, but you could plot the density of particles and the conductivity in the picture would be roughly the same, except for the values on the axis. And the point is that you see values not just at the integers from the slide before, but also at fraction values. So fractional 1, 2, and 3 would be at 1, 1/2, 1/3, and you see them here. They correspond to 1, 2, 3, and 4. You see these plateaus, but you see it also at values like this one, which correspond to fractions, not an integer, but 2/5, is particularly in white, and 1/3, which is also not an integer, but a fraction now. Now this will not be considered here, and this is certainly see the solution of course. I have to come up with some excuses. So it relies on interacting particles. So different baskets between people like Serena. And it's mathematically more diverse than the integer quantum Hall effect. So there is what I mean is a variety of approaches, somewhat even conflicting to one another. And one more thing I would like to say is that many more recent developments in the field, they branched off actually from the integer quantum Hall effect, they're cousins of the integer quantum Hall effect, not from the fractional quantum Hall effect. So we saw some point not going to that, and also just for limits of time, I'm not going to talk about fractional quantum Hall effect, except for lecture. There is this out there. So let me explain how these plateaus arise, and as I anticipated, what has this got to do with disorder. So we have to know a bit about quantum mechanics and how the spectra of even single particle operators, single particle Hamiltonians to be precise, look like. So often the spectrum comes in bands. So this here on this axis I plot the spectrum in black. So this is part of the spectrum. Then there is a gap, and then it goes on with another part of the spectrum. These are called bands, these parts. But not each band is not all of one kind. There is a central region that maybe shrinks just to one point, where you have extended states, and if it's more than one point, then it will be continuous spectrum. And then there are regions, often to the sides of the band, where you have localized states, or as called pure point spectrum, more mathematically, as a result of a phenomenon called Anderson localization, which is induced by this disorder. And so there might be two sorts of gaps that you might want to distinguish. One is the spectral gap, which is obvious, there is no spectrum whatsoever. And then there is the mobility gap, which includes everything that is not continuous. Right? So it also includes this localized spectrum within the mobility. Then a key player in this explanation will be the Fermi energy. So we place it here. And this means that all states below are occupied with electrons, and all states above are empty, as dictated by Pauli states. Then let me talk about the integrated density of states. That's a function of mu. Of course, if mu ranges in this spectral gap, if it's here or there, but changes within the spectral gap, then nothing changes in the system because there being no spectrum there, you could actually add electrons. Spectrum can be added within the spectrum. If the no spectrum, no electrons can be added, like when moving mu in this range. But if you are in this black region, then as you move mu, no matter whether here or there, then you add electrons to the system, and the integrated density of states, so the total number of of electrons there are per unit area below the Fermi energy increases. Now the Hopf conductance is constant, not just here in the spectral gap, but throughout the mobility gap. How come? Because when you move the Fermi energy within this mobility gap, you may add electrons, but those electrons end up in localized states and therefore do not contribute to the transition. So it stays fixed, it stays constant, and if you out of these two variables, n and so sigma h, n and mu, you eliminate mu, and you just represent sigma h as a function of n, it goes like this. First, you see that the whole spectral gap corresponds to one value, both of n, as well as sigma h, so it's just 1 point here. Now, the black region here corresponds to a variety of values of n, because it increases throughout, but sigma h does not increase, so it still corresponds to a constant. And finally, if you get out to this region here, then both n changes, you're adding electrons, and sigma h changes because you're adding particles in conducting states, and so this increases. But the overall thing here is that there is a plateau, which is the observed plateau, and you have it because you have a mobility gap. If this black dotted thing or cross thing, come on. Okay. If this were absent, so if the whole red thing were blue, then we would just be left with 1 point and it would have no plateau. So this all is crucial for getting these patterns. I should say that there are other explanations which tell you other things in case you see them one day. But I would like to see this explanation, which is not wrong.
Yes. The definition of Fermi energy that we gave is the fact that we have at 0 temperature, right?
Yes.
And how things change when we want to know the temperature.
That's an interesting question. So when you put the positive temperature, then it's no longer the transition is no longer sharp, feel empty, but there is a so-called Fermi-Dirac distribution which goes over. So even if say your Fermi energy is here, and then there is an ever so small population of states up here and an ever so small depletion of states over there, and this has the consequence that the plateau is not quite a plateau. There isn't a slight deviation from it. It is exponentially small, so at 0 temperature, and therefore you still observe it. But it is a fact that this experiment has to be carried out at very low temperature. Okay. Okay, so up here you just see what said, and now I'm going to tell you some kind of a little preview of the kinds of mathematics we might use to deal with this. If you have a periodic system or crystalline medium, then there is no disorder. And still, when you say that, then we can go home. Not quite. So it is only this blue point, there is no plateau, but we may still wonder at which height is this plateau, because this gives us an image. And then even without carrying out the details, we know that when we add the disorder, we know at which height the plateau will arise. So in this kind of thing, you may not want to do each and every detail at the most mathematical level. You may sometimes try to understand some aspects completely mathematically and rely on more heuristic aspects for their generalization. Okay, so for a periodic system, but there is no disorder. Log theory explains how these integers come about, and this in turn has something to do with vector bundles. This goes back to Paulus, who discovered this notion as a physicist and independent from the mathematicians. In this case, the gap is spectrum, as there is no dispute. There is a theory which has been developed also for disordered media, And the other method of choice is some form of non-commutative geometry, as it has been advocated by Willy Sarg, Schutz, Valdes, and others, going back to theories of Kant. However, did not apply them himself to the topology. Avron and Simon revisited them. And in this case, the Fermi energy may lie in a mobility gap, or you may still consider the spectrum gap between diffusion. So this is just a little overview of tools available. And then, even when you stick to the integer quantum polyfet, there are various interpretations of which we shall review. There is the bulk, which in a sense is the one that Towles used originally. There is one where you view it as a pump. This goes by the name of Laughlin, don't forget that. And there is another approach going back to Halperin. And at first they all look completely different. And you can try to relate them as but I should also say that these topics have been picked up also by mathematical physicists, and their names are in square brackets. Let me here just give you an idea what the different approaches are. So the one is the pump, the Laughlin pump. It goes like this. So, you know, the sigma p we said was quantized in units of 1 or 2 pi. So let's try to understand why 2 pi sigma p is an integer. It goes like this. Take this ribbon. So your sample is now in guise of a ribbon, turned like this, and it is threaded by a magnetic flux. So there might be also a magnetic field we saw before, just sticking out of that ribbon all the way, still there. But our focus will now be on an additional magnetic field in guise of flux threading the ribbon. And what we do is we increase this flux by 1 quantum of flux, that is by 2 pi. And what is special about 2 pi as compared to any other number, which is not the multiple of 2 pi, where it is, if you do 2 pi, then the Hamiltonian describing those particles in the ribbon, with and without that additional flux, are unitarily conjugated to one another by some unitary U that we shall describe. And then physically, when you increase this flow steadily, then what happens is that some electrons that were at this left edge of the ribbon migrate to the right edge of the ribbon. And every time you repeat this experiment, it's the very same number of electrons that migrate, not probabilistically distributed. And that number is this, gives the quantization of this whole conductance in this first understanding as a pump. Let's move to the second understanding as a bulk. So then it goes by the Kubo formula for conductivity. And it's in a sense pretty much as what I showed you at the beginning. You apply a weak electric field throughout the bulk, and transversely to it, the current density starts to flow. And there are formulas for describing the response of a system to a weak driving, known as Kubo formula. And it turns out that this 2 pi sigma b is in some way a Chern number, which is a topological invariant. And we'll see that. And then there is another idea, which I also briefly alluded to at the beginning, but I said there are current flowing at the edges of the sample. And so if you increase the say the Fermi energy at the edge by 1 unit, then there are more electrons in the boundary flowing along it, and the current increases, and the rate of increase, as it does with increasing Fermi energy at the boundary, gives also a notion of conductivity, and that's sigma h. And the reason for quantization is that that is just the number of quantum edge channels you have at the boundary. And then you can, if you're a mathematical physicist, you can accept these definitions and try to understand why they are the same. This gives rise to a certain number of theorems. You can write these theorems both in the regime where you have a spectral gap or in the more difficult regime where you have a mobility gap. So you get theorems like those. So here I'd like to tell you emissions in ocean rate. Let me put 2 minutes of 3 minutes of then let me try to put bulk versus stage in correspondence, even though just a heuristic correspondence. So this picture we saw it before. First is what happens when you have a P field and no electric field. So charge carriers just turn in a circle. But if you add the E field, then they start drifting transversely. And so if the bulk is infinitely extended, that's what happens all over the place. But if there are edges to the system, then particles are confined, like by walls that are impenetrable. And so these particles, as they drift, even they would just like to do that, thing on the left. Again, they would just like to do that, but as they hit the boundary, they intercept it, and then they bounce like this, and they move on while keeping the edge on their right. But if they keep their edge on the right here as well, the overall motion is to the left. And so the voltage difference so the interpretation here is not in the bulk effect. You say there is a voltage difference. This comes about because there is an electric field all over the place. No. Here we say there is no electric field. We just say that edge state on this edge are populated to a different Fermi level, to a different voltage than the different electric potential, I should say, than those on the other edge. And so the current, even if any single electron carries as much current here to the right as any single electron to the left, there being more here than there is a current to the right. That is another picture for the right flowing current. And this is another picture for the same effect. So that is the comparison between bulk and edge. Okay, so that was about the mother of all topological matter, which is the quantum Hall effect. And then as things go, since and that was in the early 2000s, topological insulators came up. And it is big the time for let me explain that in the next slide. It's 10 minutes or so, we can now show the context of a Hall effect. And we'll return to them in later sections, like here, where I will say something about this non-commutative geometry approach, and then also how the approach which applies to periodic media, which relies on vector bounding. This will come later. But for now, I'd like to depart because in this first chapter, I would like to give an overview on the beginning to the present days. So, topological insulators, what are they? So, we have this idea of quantum Hall effect, and it will turn out to be one of the topological insulators. But we would like to get rid of everything except the essential concepts. So, what are the essential concepts? We get rid of the magnetic field. We would like to get rid of this particular orbits, which had some explanation, explanatory moment. We'd like to get rid even of the 2 dimensions, and we'd like to keep the essence. So here is an attempt to find out what the essence is. So topological insulator is a sort of vague definition. So it's an insulator in the body. That's a property we want to take. So it has an excitation gap. If the Fermi energy is like this, these states are occupied and these are occupied, there is an excitation gap from getting an electron from here to a higher energy. You don't get it at zero cost. For independent electrons, as they are depicted here, so it's a spectral gap at the Fermi energy. Let's make it a little bit simpler and say spectral gap, not just a mobility. Okay? And then there is topology. So where does that come from? So suppose you have a space of any importance. It could have been in the case before, describing samples, different samples having all the quantum Hall effect. And now you would like to start to deform them into one another. And you ask yourself whether you can deform such a topological insulator for completeness, the quantum Hall system, into an ordinary thing that is a system that in particular doesn't have a quantum Hall effect, or more generally in the ordinary topological insulator, whatever that means, while keeping the gap open, not by closing the gap, but by keeping the gap open. So that's the notion of homotopy. We want to change one thing in another, but with some rules in place, like the gap shall be open. Now, this definition calls for the question, what is an ordinary insulator? So by an ordinary insulator, we think of one that can be deformed to the limit of well separated. So you have a sample that has its atoms, and then we think one in which the separations are a little bit bigger and ever larger. And so in this limit, we call it a trivial, an ordinary topological insulator, which actually is not a topological insulator, an ordinary. In fact, what you have is, if you view it locally, is the void. So the void is a trivial topological insulator, or ordinary necessarily. Okay, and topological Hamiltonians may be inequivalent. For instance, if you think back to the quantum Hall effect, if you have it, if your Fermi energy was here, you may have had a certain corresponding to a certain plateau here, there, or to a certain plateau. But if it were there, the value of the plateau was another one, and it was they were not equivalent, because if you wanted to move the mu from here to there, you would have to place it in a place where there was no gap. So the change from one to another was not a homotopic one, and topological, so even a topological insulator with a certain quantum Hall conductance and another one are inequivalent. And so you come up with a classification into classes. But you try to forget that this in particular quantum Hall. It's more abstract. The analogy of homotopic and impossible deformation is we cannot change the topos to a sphere as long as it insists that the whole topos remains there. And so they differ by genus. You don't have, when you come up with the inequivalence, it's not that you decide they are different because you try in all possible ways. You look at them and you see that they have a different genus, so you already know that it never will be possible to deform one to the other. In the case of the quantum Hall effect, it was this number 2 pi sigma h, essentially the whole conductance, that would tell classes apart, that the value of that thing would be one integer rather than another. And so one refinement that makes this story somewhat interesting is that the Hamiltonians may enjoy a symmetry which has to be preserved under the definitions. So what does it mean that you ask only for topological insulators which enjoy a symmetry? First, it means something negative, that you just look at the subclass of the one you were looking from before. Those enjoying the symmetry. So maybe these two enjoy the symmetry, but everybody else doesn't. And then you can ask, can I deform this into that one? And this is a different question than before. Even if the whole class of topological insulators without symmetry, they were deformable. They are maybe not deformable within the smaller class of those which do enjoy this. So it makes the problem poorer because you look at less object, but also richer because the notion of homotopy has changed by that means. They have finer classes. And let's look in particular at what Paul Gage correspondence means in this language. Can no longer mean what it meant before with these orbits. What did it mean before? That orbits would drift to the right all across the bulk, or there would be one thing, or there would bounce up at the edge of the other. So here is what it would mean. So here is just what I said before, that you want to keep the gap open and respect the symmetry while you deform these Hamiltonians. So suppose you have such a deformation of Hamiltonians. Yes, please.
I have a question. We're talking about the insulator.
Yes.
Is this somehow for a given family level mu I have to insulate, or how I have to think about it?
You could. In fact, yes, for a given value of mu, you have an insulet. The mu is part of the definition of the insulet,
Yes.
which means that actually keeping the same piece of matter by changing the mu is passing from one topological insulator to another. Right? And so it may end up in different classes. This was sort of tacit in what I said, but confusing what I didn't say. Okay, so is this the first thing? So this is what the thing here. And so here we suppose we have here a topological insulator on the left, and here you have an ordinary insulator. And now the interpolation that you thought abstract in the space of Hamiltonians, you think of it as interpolating materials that are present in physical space. And now, since that the topological insulator cannot be deformed into the ordinary one while keeping the gap open, somewhere in between, the gap must have closed. We assume that the symmetry is kept in place. So it must be the gap that has been closed somewhere. And so the spectrum must have hit the Fermi energy mu. And therefore we have interface energies, interface states at somewhere here in the middle. So states at the Fermi energy in the spectrum. Somewhere here, perhaps here or perhaps there, we don't know. But somewhere there must be, because otherwise this would go against the possibility of deforming one to the other with the gap on. And so if we replace the ordinary insulator we just had, the ordinary insulator we just had here by the void, which is in the same class by definition, so we can put there the void, then an interface state between the topological insulator and the void would be appropriately called an edge state. And so this means that at the boundary of topological insulators, you find edge states at the Fermi energy, pretty much as in the picture I listed. The bulk edge correspondence is the determination of bulk by a topological insulator implies the existence of edge states. Converse is not quite true, but then.
Sorry.
Yes.
If I can interrupt you, just to see if I understand correctly. So here we are talking about physical space deformations. So we have like two materials and then something joining them on real space.
Yes. Yes. So originally it was in the space of Hamiltonians, but now in order to get to my argument, I want to think that this deformation occurs by having one material, then there's one stiff slide and so on and so forth. But this abstract deformation is embodied in physical space. But it is just what we had. And this means that when breaking a topological insulator into two, the newly created surfaces are conducted, because there are states at the Fermi energy. So here is the picture. First, there is only conductive states at the boundary. And afterwards, if you break, then you have conductive states even at the newly created surfaces. Okay, and then the next topic is the periodic table of topological maps. This was a definition made of thin air. Just try to keep the abstract out. This seems to be important. But now, what kind of topological map can you do? So let me guide you into this. It's starting again from the integer quantum Hall effect we mentioned. There we saw that what distinguishes different classes, the value of the whole conductance, it's an integer, and they tell different phases apart because you cannot move continuously from one integer to another. And so the classes, different classes are labeled by integers. At least maybe there is a final classification, but at least integers make some distinction into different classes. And what says the index group is C, the integers. In symmetries, we said define the classes, or as physicists say, there are symmetry protected phases. So here, the different homotopy classes could be called phases in the physics language. And here we would have symmetry protected phases. Now, which symmetries shall we pick in order to make this classification? This is to some extent a matter of choice, but also by historic reasons, the people looked at involution. So kind of symmetries that if you apply it twice, you're back at the identity. This goes back to a tradition by Dyson, in other context, that then close to this one, Altland and more recently, at least Altland and Zirnbauer. And here are the evolutions people usually consider. One is time reversal theta. One is charge conjugation. Not all systems possess charge conjugation. But we look at those who do possess charge conjugation. That's it. And then you could look at the product of two, right? Pi, theta times sigma. And that's called, for reasons that we may or may not see, chiral or sublattice symmetry. And you can have them alone, so just theta or just sigma. But if you have them both, you also have pi by necessity. But you can have pi, just pi, without having neither theta nor sigma. Still a possible symmetry. But what is clear, in this little context here, is that when you have any two of them, there being all involutions, then you have all three of them. And so here are a few examples. When you have no symmetries, that's just the quantum Hall effect we discussed before. And then you can have time reversal symmetry in 2 dimensions. That's, to be precise, a not, and we can come to that, a not time reversal. They're still in dimension 2. And this is then called the spin quantum Hall effect. It has been discussed by Molenkamp and his contribution by theoreticians like Schutz and Zahn and Andrei Bernelik. There is charge conjugation, which is present in some superconductors, this time in T equals 1. And maybe we'll come to that. It's a model for that is the Kitaev chain. And now this is presently investigated at Microsoft, all these big companies that were involved in quantum computation. And they bet on this horse, on superconductors and dimension T equals 1, to construct the qubits on which to make manipulations. So that would be, the symmetry would be charge conjugation, and we would be in dimension T equals 1. And then there are the chiral ones, these ones. There are some change. There's not something to do with polaritons in the experiment. In T equal 1, there are experiments by Jacopo Canusotto, Jacqueline Bloch, and others. So, in these cases, how are the homotopy classes laid? In the good old quantum Hall effect, we know it's labeled by integers, and the index for is C. But what are they labeled here, and what is the index? To all these questions, there is one answer, which is summarized in this somewhat celebrated table called the Kitaev table. And it goes like this. So here this is a label for the different type of symmetries. Forget them. I'm not going to explain why they are labeled like this. But just take them as labels. It has something to do with Lie groups. What I do explain is the symmetry. We just saw it. Theta time reversal, sigma, particle Hall symmetry, and pi, the product of them, the chiral symmetry, which can also come as a standalone. And then what do these little numbers mean? 0 means they're absent. Okay, none of them is present in this first row. And for instance, in the next row, just the chiral one is present, but not theta and sigma. Then if you go down, you can also see that there are minus ones, not just ones and zeros. How does this come? So here, what do we expect from a symmetry to fulfill? Say theta time reversal is an anti-unitary operation. It's implemented anti-unitary quantum mechanics that commutes with the Hamiltonian, with the single particle Hamiltonian. And depending on cases, sorry, in quantum mechanics, theta can square to plus or minus 1. So even when it's minus 1, consider it as the huge. It just means that if you put the phase on state on a vector, which does not change the quantum mechanical state. So it's it's acceptable to call it an evolution. Then, so when there is presence, and it is in this case, the square is 1, that's called even time reversal, then you would find a 1, like you would find it here. But when it's present, the square is -1, like here, then you would write the -1. And then comes charge conjugation. It's also an anti-unitary operation, but this time it anti-commutes with the single particle Hamilton H. And likewise, it can square to +1 or to -1. And then there is the product of the two, which being the product of two anti-unitaries with ones is unitary, and we assume that the two symmetries, if they're both present, they are commute and give pi, or else pi will stand alone. And so here is the possible combination that makes 10 combinations. As I said, it's not possible to have 2, but not the third one, because that would also imply. And here are the possible classes. And then what you see here is the index. So often, very often you see a 0. This means there is nothing in this. All topological insulators of that particular description are in one class, the trivial one, so it's not even worth to call them topology. But for instance, here, no symmetry, dimension d = 2, that should be our quantum Hall effect, and indeed you see the C appearing in the tape. Then it goes on, and then there is another class, which is just, staggered with respect to the first line. So whenever we have a 0, now we have a C. That's like this, and it repeats with periodicity 2. So these two classes, they're sort of a group by themselves, hence this line under that. And then, I didn't say this, sorry. But maybe you figured it out. I said it in past. So this is the dimension of space in which this material is supposed to live. 1, 2, 3, up to 8. Of course, it's somewhat theoretical because we do not go beyond 2 or 3, even though there are people who, this dimension has not to be understood always as the literal physical dimension of the space. They can bring it up in synthetic ways. So the table is not strictly limited to 3 dimensions, but doesn't go much further, right? And then there are these classes here, which also have a periodicity, but in this case, the periodicity is 1. So what you see here is that there is this constancy along these diagonals, which is a feature of this thing. What the brief word on the history of that. So first version came from Schneider and Shinsen-Yu, and then they had it, but not in this order here. So this diagonal periodicity was not seen. And then Kitaev came, based on previous work in another work in a completely different context, standard matrices by Alker and Zirnbauer. And this was based on block theory. And this block theory reminds one of vector bundles. And mathematicians had a classification of vector bundles, which was that. So he realized that basically just somewhat copied what mathematicians had found decades ago. So this was found first in the periodic case, but then there is the non-periodic case where you have these non-commutative notions, the index formula, and they've been found by Godin, Schutz, Landes, pretty much for all cases in this thing. And so here you see the special case we might consider in this series of lecture. So in a sense, this one we already did, at least to some extent. We hopefully, I'd like to be cautious, anything hopefully. I'd like to look at this one, it is a parallel chain. This is this Kitaev chain, where the index is C2. By the way, what is C2? C2 is just a group with 2 elements, plus and minus 1. If you want to read it multiplicatively, 0, 1 if you want to read it additively. And this, I think this is more sure that we get to that one. That's odd time reversal. There the index is also C2. And then perhaps there's one more which doesn't fit into the table. you might also now, how is it? Now half an hour
Yeah.
into so I still have 15 minutes. So let's now become slightly more mathematical and not too
Yeah,
much.
so can I ask a question about the table?
Yes.
No, out of curiosity, I believe that probably this symmetry, theta sigma pi, are related to the setting with the magnetic field and so on, but there are some kind of classification which are the symmetries.
Yes. So later on, people had specific cases, and they say we want to look at one space group so the symmetry, the particular, how should I say a particular space group, it's a notion from crystallography, shall be our symmetry. That's our symmetry. Then let's do a classification. You can do it. There have been 230 space groups in three-dimensional. Who knows how many other is the name? That's the name. Has been some interesting in this topic. I think it's certainly interesting to someone has understand the questions for what symmetries and just which in sense in I say one law which has something to do with Floquet system, where it's not so much about Hamiltonians, but it's about unitaries. Okay, another question. Well, let's return basically back to the quantum Hall effect of what has been given. And let's just try to become a little bit more mathematical and also bring this different perspectives in connection with one another by way of some things. So here are the various approaches. This is just not to give the impression that they're covering the whole thing. So there is originally people have not studied much Landau Hamiltonians, but this is just a three-particle order, then there being a homogeneous magnetic. We'll not discuss that. Periodic Hamiltonians, yes, we will do that. And then the role of disordered non-commutative geometry, and we develop the theoretical kinetic state in a somewhat pedestrian. And then there are completely different approaches. Effective field theories are important and should not be discussed here. You are specialists of effective field theories. We go back to Weyl and others. So here is a somewhat pedestrian mathematical setting, but why not? So we based the discussion on a microscopic model, so that's not the case in so concretely a Schrödinger operator. It describes single particles. Of course, you can conceive many, but they're all independent. And your plane is actually a lattice. Here is an hexagonal lattice, but you can think of a quadratic lattice. And then you have lattice points, x, which have two coordinates, x1 and x2, which you can fill both as integers, labeling a point, labeling a lattice point. Then you have single particles Hamiltonians, HB. These are operators from the little L2 space of gamma. So is this it's going the wrong way. Is this a familiar notion, a little L2 of gamma? Should I explain what this is? So gamma, let's say, is just Z2 and L2 of gamma and Z2. These are just functions, psi from Z2 to C, so complex valued functions, such that the sum of all lattice points of psi n squared is 5. So that's just the most obvious analogy to the L2 space of real line of the it's called a lattice, and it's technically somewhat similar. Some technical points continue up. And then there is a self-adjoint operator there. the Hamiltonian. And so you can think of this as somewhat naive, but probably you know how to make the thing as a huge matrix. So, where for each side there is both a row and a column, and you have a matrix element HP of x prime and x, and somehow the physical interpretation of it is that this is infinite. To think of the Schrödinger equation, this is the some probability amplitude that in the next time dt you would hop from x, if you are there, to the side x prime. The idea is that this is short range in x minus x prime. You don't hop very far in infinitesimal time. That's so-called tight binding. And we apply this to infinite systems. So in order to define our indices correctly, it is important that the lattice is infinite and not a finite set. It's the thermodynamic limit, as they say. And preferably, we should look at Hamiltonian that incorporates some kind of disorder, but not always. And then the Fermi energy should lie in the spectral or mobility. Now, what is the concrete technical effect of having a mobility gap? Mobility is this. So, given your Hamiltonian and given your Fermi energy minimum, you can look at the spectral projection, that's this thing, corresponding to the interval from minus infinity all the way to the Fermi energy. So that projects to all states that have an energy in terms of the Hamiltonian HP that is less or equal than less than V. It's a projector. It's called the Fermi projector because it physically it's the Fermi C. Oh, sorry, making a mess. It corresponds to the Fermi C in that it projects to all states that are part of the Fermi C. And then the assumption, which is a reflection of this ability, is that this is also short range in the following sense that even so, if you fix one x prime and multiply this thing here by something exponentially increasing in the separation, well, this is so decaying in the separation that this is summable, and in fact, almost uniformly bounded in the point x prime, on which it was not summed, except that it might grow very slightly and it takes an arbitrary small exponential decay of rate epsilon to make this supremum over x prime length. That's what the mobility gap allows you to have. So this means that the points x and x prime have to be very close to one another, or else this matrix element is less. And so this property is trivially true. If HP is a multiplication operator in position space, you would consider such a Hamiltonian, but just for the sake of understanding what's going on, if HP is a multiplication operator, so just as a diagonal matrix element, then so does the Fermi projection. And then this is diagonal to begin with. It outcomes for free. But if HP is a function of momentum, think of a free particle. Doesn't localize. And indeed, if HP is a free particle, then the corresponding Fermi projections from, say, the origin to some point that still decays, but it decays fairly slowly, just like it has a polynomial decay, and therefore it does not satisfy this fast decay. In this property here is proven in virtually all cases where localization, Anderson localization is. So we will rely on that. Now, well, it's still 5 minutes. Now, here is something embarrassed about telling you this. Because it's just some basic things about quantum mechanism. If anybody is familiar with quantum mechanics in places, just skip it. Skip it. So then we could go. So if you have an observable x, then the rate of change of x is another observable, which is still very important. And if it's not clear at the pace of taking, just object. The other thing, and then is just the explanation for that, and the other is a two-man second quantization for firmness. So there are single particle space and states, so psi, and then there are many particle states. You don't want to describe one particle that's zillions, but it's infinitely many because they extend all of the space. But you can still talk of a single particle margin, one particle density matrix that's an operator on the single particle space, which is a Hermitian or self-adjoint operator. And for Fermi's, this comes from Fermi's, this is between 0 and 1. And the meaning of it is that it tells the expected occupation of any single particle state in the many particle state. You compute this is the average occupation of psi, and it's a number between 0 and 1. If it's not okay, you tell me. And this is more conveniently in terms of projection onto this single particle state, and that's the Now, if you have a single particle observable, you skip this, and then you can take the expectation value of that single particle observable in the many particle state. So that means you count x, no matter from which particle it comes, and then the expected the expectation value is the base of x times 1. I'm skipping the derivation. That's, and if it's not found, I will spend last minutes. And there is the detour in electromagnetism. It's about gauge transformations. So it's just in mind, you have like magnetic fields, like electric and magnetic fields, and then you can describe them in terms of electromagnetic scalar and vector potential, like this formula here. And by given E and P, defined they are not unique, but they are unique onto gauge transformations, which is here. You go from phi to pi to wave by pi, and the transformations are generated by an arbitrary function of space and time. Right? And they leave E and P invariant. But they also have a reflection of quantum mechanics. So suppose you have a Hamiltonian like this one. And for a charged particle in electromagnetic field, it's not quite that. You would, instead of P, you would use P minus A. And then the other thing I wanted to tell you, if you make a gauge transformation, then the Hamiltonian is also affected by this gauge transformation. It goes like this, that the state psi changes to e to the I chi psi, and chi is this generating function. And it has an effect. So this is the transformation on states, and then on Hamiltonians is in the adjoint action. So it goes by having H conjugated by that U here, U which is e to the I chi, and you get to a new H. So that's that, and it can go through this slide slow, but probably have seen this. If not, see some faces which are.
Maybe the commutator, the role of the commutator, I don't think we saw it in the class.
Okay, thanks, sorry.
My fault.
We completely.
I mean, the fact that the change in the server. Since it's an easy thing, maybe.
Where is the
Yeah.
it's one before. Yeah. So this is the Heisenberg picture, or maybe it depends on how you want to say. So the expectation is this, the expectation of an observance. So in a sense, we know observance because we can compute probabilities and particular expectations. So the state changes in time like this is the property. Right? And so at the later time, forget the derivative in front, at the later time, the expectation is that. And now, how does it change in time? Say it's still at time t equals 0. But then it take this derivative. There are two reasons for change. So you use the product rule. One brings down an h here, which you could bring over because it's self-adjoint, and that gives h times x. But it could also hit here, that gives x times h. And by bringing over this minus side from here to there, it becomes a plus side, but here but not there. So you get this commutator, and therefore the observer which describes the rate of change is given by the commutator. Let's make an example which we shall use. So if X is charge, maybe you have a region. You have a region in space, and you're asking how much charge is there in that region. Well, the rate of change is given by the current across the boundary of that region. And so if X is charged, then the current through the boundary is this commutator. IH commutator. That's all it is. We will use the current as an observer coming from a charge, therefore this is made. Okay. Now I think I should not abuse your patience, and this is also in a sense a cut. Just introduce some general notions of physics, which we might then use Thursday when when discussing the integer quantum Hall effect as a problem. Okay, for now that's it.
Thank you very much.